Recently, the drill of the Perseverance rover cut into a rock called Cheyava Falls, revealing a pattern that forced NASA to convene an emergency meeting of its top astrobiologists. Inside the rock are dozens of millimeter-wide dark circles, ringed by white calcium sulfate. To researchers, these look exactly like the leopard spots found in ancient sedimentary rocks on Earth. On Earth, microbes use redox reactions to turn environmental chemistry into metabolic fuel, leaving dark mineral scars. NASA confirmed the Martian spots contain these exact complex organic molecules, the carbon chains forming the basis of life. If these chemical signatures are truly biological, they represent a set of evidence more complex and convincing than anything we have ever seen in a single Martian rock. However, the discovery immediately hit a wall. Right next to those organic spots, the rover found large crystals of olivine. Olivine is a mineral born in volcanic magma at temperatures exceeding 1,000 degrees Celsius. These are conditions that would instantly incinerate any organic matter. This creates a paradox. Either the rock preserves a form of biology that survived a volcanic environment, or inanimate nature managed to perfectly imitate the physical traces of life. One theory suggests a chemical forgery. Over centuries, superheated, metal-saturated groundwater could have seeped through the rock, depositing mineral rings that are indistinguishable from biological fossils. To determine if these spots are an ancient feast or a geological trick, we have to investigate the violent history of the planet itself. 3.5 billion years ago, Mars was not a desert. It was a world of flowing river deltas, deep oceans, and a thick atmosphere capable of trapping heat. This habitable environment was maintained by the geodynamo effect. Deep inside Mars, a churning liquid metal core generated a massive magnetic shield that protected the planet from the sun. This field acted as a barrier, deflecting destructive solar winds and allowing liquid water to remain stable on the surface for millions of years. But Mars is smaller than Earth, which meant its core cooled and solidified much faster. As the liquid metals stopped moving, the geodynamo shut down, and the magnetic field collapsed. Without that internal engine, the planet lost its protection. The surface was suddenly exposed to the full force of solar radiation, ending the era of Martian habitability. With the magnetic shield gone, the sun's unyielding radiation began to dismantle the Martian atmosphere, molecule by molecule. This is atmospheric sputtering. The solar wind physically collides with unprotected gases, stripping away the atmosphere and venting it into space. As the air thinned, the surface pressure dropped. The planet's water either sublimated into the void or flash froze into massive ice reserves hidden deep underground. This planetary collapse created the irradiated, frozen wasteland that preserved the paradoxical minerals found inside Cheyava Falls. Today, that same hostile environment is the greatest obstacle for human exploration. But the chemistry that makes Mars a graveyard is exactly what we will use to stay alive. We cannot rely on a multi-billion-dollar supply chain from Earth. Instead, we must use in situ resource utilization, engineering our survival directly from the Martian environment. To find water, settlers will tap into the massive reserves of subglacial ice buried beneath geological features like the Valles Marineris canyon system. To create air, the MOXIE device forcefully separates oxygen atoms from toxic carbon dioxide, producing breathable O2. That same CO2 provides carbon for fuel. Combined with hydrogen from ice, engineers produce liquid methane to power return rockets. The very processes that destroyed the ancient Martian biosphere are now being repurposed as the tools to resurrect human life on its surface. The upcoming Mars sample return mission will be the final test. Only by analyzing Cheyava Falls in a laboratory can we confirm if those spots are biological or a geological trick. The race to recover these samples has become a high-stakes geopolitical competition, as nations vie to be the first to successfully launch a rocket from the surface of another planet. Even if the leopard spots prove inanimate, the engineering required to go and get them grants us the ability to launch from multiple worlds, changing our status in the solar system forever. Mars's history reveals the fragility of a living world, but its chemistry provides the building blocks for a future where humanity exists on more than one planet.